So the big question is, how do you pronounce this guy's name? And I guess you got to start with, how do you even spell his name? So the great website source for everything, Wikipedia, lists two different spellings. Now the second one seems to have come into vogue recently, but the one that I've always known is L'Hôpital's rule. But I think, I don't know, somebody who speaks French could tell me. I think his name does translate to hospital, but on the test, now I've done this before. I've given you extra credit for people who can spell the name with punctuation, spell it correctly. L'Hôpital, all right? No S. Don't put an S in there unless you want to annoy me, which isn't a good thing to do when I'm grading your test. All right. Regardless of how you pronounce it, L'Hôpitals, hospitals, his rule is actually really powerful. And what's weird for me is that we're teaching this in Calc 1. It's like giving a second grader a graphing calculator and saying, here you go. I mean, this has always been in our Calc 2 course, so it's weird for me to see it in Calc 1. But let's take a look at it. So here's L'Hôpital's rule. Yeah, we're back to limits. And this is actually really cool. It's a really cool rule. L'Hôpital himself did not actually discover it. Johann Bernoulli discovered it, but they had some kind of an interesting arrangement by which L'Hôpital paid Bernoulli for the right to publish his discoveries. So it became, L'Hôpital's rule instead of Bernoulli's rule. It was discovered in like 1690 something, 1696 maybe. In any case, what it says is if you have a function of indeterminate form in the limit, so that is either 0 over 0 or infinity over infinity, one of those two cases, then in order to evaluate the limit, you can take derivatives. Take the derivative of the numerator and take the derivative of the denominator. Don't use the quotient rule as you do this. Just differentiate each of them separately. So, okay, let's give it a shot. Let's try L'Hôpital's rule, but if it's something of indeterminate form, then we can apply L'Hôpital's rule. So, all right, that was page 305. Okay, so let's start with problem number 12. And we'll do it a couple different ways. Problem number 12. So we've got the limit as x approaches 1/2 of 6x squared plus 5x minus 4 over 4x squared plus 16x minus 9. Now the one tempting thing is, it's 6 over 4. But why can't we do just, it's 6 over 4 because the degrees are equal? How come I can't take that shortcut here? Well done. Excellent. The limit's not going towards infinity. We're going to a finite number. If it's going towards infinity, out towards infinity, this is going to become 6 over 4 or 3/2. So let's take a look at it graphically. So here's our graph, and we want to know what happens to this graph as we get close to x's 1/2. And it looks like, all right, right there at 1/2, it's undefined. That's not a big surprise, but it looks like it has a limit. Getting closer and closer to something, 0.5 something. But let's see it a different way. Now you can do it with a graphing calculator numerically, but let's do it kind of old school for the moment. What if I factored this and did the limit as x approaches 1/2, and let's think, that's going to factor as 2x minus 1 times 3x plus 4 over 2x minus 1 times 2x plus 9. Okay. Well, as long as you're staying away from x equal 1/2, we can cancel these things out and just look at the limit. So it's going to be the limit as x approaches 1/2 of 3x plus 4 over 2x plus 9. So 1.5 plus 4 is 5.5 over 10, or basically 0.55. Does that match with what we saw from our graph? Yeah, it looked pretty reasonable. Those values were getting close to about 0.55. We could zoom in a little bit and see that, but that looks okay. This is nonetheless a case for which L'Hopital's rule could be applied. Now, I think the book and the instructions for the problems here kind of urges you, don't necessarily use L'Hopital's rule just willy-nilly. Be thoughtful about it, okay? In this case, we don't really need it, but if you did want to, we could use it. So let's take a look at L'Hopital's rule in this case. In the numerator, you've got a function. In the denominator, you've got a function. This turns into the 0 over 0 case, because if you typed in, or if you plugged in 1/2, the numerator term would be 0, so would the denominator term be 0. So this would equal the limit as x approaches 1/2. What's the derivative of the numerator? Thank you. Yes, if I plugged in 1/2, the numerator would be 0, and the denominator would be 0. That makes it an indeterminate form, so that's why I can apply L'Hopital's rule. L'Hopital's rule. Yeah, because that's a 0 over 0 indeterminate form. Okay, let's see about the denominator. Derivative of the denominator, that's going to be 8x plus 16. And if I plug in 1/2 now, is it okay to plug in 1/2? Is it going to give me any problems? No, it should be okay. I'll get 11 over 20, which is, again, 0.55. So, cool. It works. So it's actually pretty nice. One of the problems that we didn't really prove in this course earlier was this one. The limit as theta approaches 0 of the sine of theta over theta. So this one, for example. With all your limit problems, the first thing you always try is to plug in a limit. If it works, great, you're done. And there are problems on your old test and problems on the final where it's just going to be plug in the limit and you'll be done. But if you plug in the limit here, sine of 0 is 0, and, well, you have 0 in the denominator, right? So it doesn't work. You have a 0 over 0 case. But at least it's nice because that's an indeterminate form. So what that's saying is that I can take the limit of the derivative of the numerator and the derivative of the denominator. Now I'm going to differentiate with respect to theta. What do I get in the numerator? Cosine theta. Someone be brave for the denominator. 1. Thank you. So, okay. Well, what happens as theta approaches 0? Can I plug in 0 here? What's the cosine of 0? 1. Wow. Earlier this semester, had we taken the time to prove this, this is like a 10 or 15 minute proof where you use the squeeze theorem and you have an upper limit and lower limit for the function and you squeeze it to 1. It's like a 10-minute job to prove this thing. We did it. We could do it, but I think you want to get out on time. So let's just stay here. But it's nice. L'Hopital's rule is really nice. Now, why don't you try one here real quick? The limit as x approaches 3 of x minus 3 over x squared minus 9. Find that limit. Good sound effects. I wonder if my mic picked that up. So I'm curious. There's a couple different routes you can go. Actually, a lot of different ways we can solve this. Did anyone factor this one? Solve it by factoring? Yeah. Nothing wrong with solving this one by factoring. In fact, that's probably what I would do first. Is just say, okay, well, this one's going to factor pretty nice. You got x minus 3 over x minus 3 times x plus 3. These things cancel, and I'm left with the limit as x approaches 3 of 1 over x plus 3, which is 1/6. Great. There's nothing wrong with looking at it on a table. You can look at it on a table, plug that function into your calculator, and see that, 2.5, 2.8, 2.9, 2.999, etc. You're getting close to the decimal value for 1 divided by 6. Okay. But last but not least, you could take out a sledgehammer to swat this fly, and it would work, right? This is 0 over 0. It's an indeterminate form. So if we did that, show of hands. How many did L'Hopital's rule on this one? All right. A few people feeling sheepish, like, yeah, okay, I did this. Look, it's not wrong. It's just, I don't know. It's just kind of weird for me teaching that in this course. So it's going to be 2x. Well, just 2x, right? 2x minus 0. So plug it in, you get 1/6 again. At least we're getting consistent confirming results. You should, in doing it in different ways. How are we looking here? Good, Brandon? You could say something like, 0 over 0, apply L'Hopital's rule. That's fine. But I'll look at your work and I'll see that you applied L'Hopital's rule, because it's going to be clear that you're working with a derivative. So, yeah. So I guess the short answer is I don't really need to see anything special. But if you do put in stuff like that, it helps me in your grading, and it helps me give you more partial credit points in case you make a tiny mistake. So, yeah. Thank you. Anything else on problem number 8 here? Okay. Well, let's see about some other problems. Problem number 14. Limit as x approaches 0 of the tangent of 3x divided by the sine of 2x. What should we try first? Yeah, plug it in. Plug it in. And you plug it in, 3 times 0 is 0. What's the tangent of 0? Do, 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 do. 0. All right, it's 0. Likewise with the sine. Sine of 0 is also 0. So this is an indeterminate form. Ends up as being, 0 over 0. And yeah, this one's going to be really hard. I don't know as though you could work this one algebraically too easily. We can't factor this one. It's no longer polynomials. So what should we do? L'Hopital's rule. Yeah, hit it with that sledgehammer. All right, in this case, it's actually a really good way to go. The one thing you got to keep in mind is that you're not applying the quotient rule here. Do not apply the quotient rule. That would be a bad thing. You want to take the derivative of the numerator. Secant squared of 3x times the derivative of the inside. And I'm going to put that 3 out in front. And likewise down here, derivative of sine of 2x, cosine of 2x, times the derivative of the inside, which is 2. So, okay. Got through that in one piece. Can I plug in the limits now? Cosine of 0 is 0. Well, for secant, secant's 1 over the cosine. Cosine of 0 is what? 1. Squared is still 1. So, yep. 3 over 2, because each of these are 1 when you plug in the limit. Hey, this works out pretty nice. Well, when you plug in the 0, it's 2 times 0, which is still 0. Yeah, so I appreciate the question, but it's cosine of 0 is 1. Okay, so far we've done the 0 over 0 type case. It'd be nice to see something in a different case, and let's do that with problem number 20. The limit as x approaches infinity of x plus x squared over 1 minus 2x squared. If you try plugging in a limit, what case do you end up with? Yeah, infinity over infinity, right? Now there's a real simple way to do this case though, right? Brandon's nodding. What do you see? Yeah, it's negative 1/2. It's just the leading coefficients, right? So you can say, oh, okay, well, the leading coefficient test, let me rewrite that as limit as x approaches infinity of x squared plus x over negative 2x squared plus 1. But yeah, it's the leading coefficient test. These things match. Our limit's going to infinity, so yeah, just negative 1/2. Let's also do it a different way. Let's also apply L'Hopital's rule. So, tau in the numerator. When I apply L'Hopital's rule here, what would I get? Just 2x, good. And in the denominator, 2x plus 1, thank you. Negative 4x, good. Now I can't quite cancel here yet, can I? So, bummer. What would happen if I tried to put in infinity? Can anyone see what's going to happen with this one? Well, but we're not going to 0. We're going to infinity. Can anyone see what's happening? I mean, you should always try plugging in a limit, but what happens when you plug in the limit again? Infinity over negative infinity. Yeah. And I probably could have put a negative here as well. But it doesn't matter if these signs match. You're getting an infinity over infinity case again. So what's that mean? Yeah, we can apply L'Hopital's rule again, which feels almost like, ooh, really? We can do that? But the answer is yeah. This is the limit as x approaches infinity. All right, somebody be brave. Do the derivative of the numerator for me. Marissa, I see a volunteer looking at me. 2 over, and this is a constant. So derivative, our limit of a constant is just a constant. Put that in lowest terms, negative 1/2. Nice. I like Brandon's approach earlier, right? I think that worked out really good. Just look at the leading coefficients. But what it's showing you, and the important thing to get, is that you can apply L'Hopital's rule repeatedly within a problem. As long as it keeps on satisfying the tenets of that, then sure, you're in good shape. How are we looking with problem number 20? Pretty good there? All right. Let's take a look at problem number 22. Limit as x approaches infinity of the ln of the square root of x over x. Now, before we start working on this with L'Hopital's rule or whatever, let's look at it graphically. This is one that I've done for us up on the website, on your link. So if you want to click on that link, you can. And then go down to problem number 22 and click the circle next to our graph. Shut off the other stuff if you have it there. Well, let's look at this. And I'm going to zoom out a little bit. What's happening to this graph as you go out the x-axis towards positive infinity? Where's it going? It's flatlining, right? It's going towards 0. So So that would be your guess before we do any calculations. And let's hope that our calculations confirm this, right? Because that certainly looks like it's going towards 0. Okay. Well, if you tried plugging in infinity, you'd get the log of infinity, which is, still going to be infinite over infinity. Over x squared? Okay. Good enough. Before we start doing this, I would make a suggestion, and that is, let's rewrite this and use the properties of logs. So that's the limit as x approaches infinity of ln. How would I rewrite this? X to the 1/2, and that 1/2 is going to come out in front. In fact, I'll take it out in front of the log and then out in front of the problem altogether. So let's write it as 1/2 the limit as x approaches infinity of the ln of x over x squared. Because a constant's not going to affect the limit. Only terms in x that are going to affect the limit. Well, at this point, I kind of need to get busy with some actual calculus. This does still satisfy L'Hopital's rule. It's the infinity over infinity case. So I can use L'Hopital's rule. Haley, can you do some derivatives for me? Good? Excellent. And that's going to be equivalent to the limit as x approaches infinity. Now that 1 over x, let's take care of it like this. This is 1 over x divided by 2x over 1. So I just kind of wrote that 1 there out of my convenience, because when you divide by a fraction, what's the rule? Multiply by the reciprocal. So I'll end up with 1 over 2x squared here. What do I get when I take this limit? Well, it'll be 1 divided by infinity. That's 0. So you get a big goose egg there. What's nice is that what we see with the graph matches our calculations. Our intuition told us that it should be going to 0, and so do our calculations. So that's a good thing. Any comments or thoughts on problem 22 here? Let's try problem 34. I guess the one good thing about introducing L'Hopital's rule in this course is that it does give you a little bit more practice with derivatives. Cosine of mx minus cosine of nx over x squared. Yeah, this is another 0 over 0 case, right? Because what's the cosine of 0? So I'll get 1 minus 1 in the numerator, which is 0. So it's a 0 over 0 case. I'm not thinking that one's going to factor very easy, so there's no algebra tricks here other than L'Hopital's rule. So see what you get when you apply L'Hopital's rule. If you're viewing this at home, I'll give you a chance to play along. We'll pause things for just a minute before we resume. 0. Sine of 0 is 0. Sine of 0 is 0. If it fits L'Hopital's rule, then you can do it again. So we're going to apply L'Hopital's rule here. So it's going to be the limit as x approaches 0 of sine of mx times the derivative of the inside. Derivative of the inside is m. It'd be negative, yeah, negative here. Because derivative of cosine is negative sine, so we get the negative out front. Likewise over here, derivative of cosine is going to be negative sine, so those negatives will cancel. It'll be plus sine of nx times the derivative of the inside, which is n, over 2x. And that doesn't seem to have gotten us anywhere, right? Because we're still at the same problem. Sine of 0 is 0. Sine of 0 is 0, so I have 0 over 0 again. That's kind of a bummer. So what am I going to do about that? Try it again. Try L'Hopital's rule again. So the limit as x approaches 0, derivative of sine is cosine, times derivative of the inside, that's going to be minus m, anyone? Squared, good. Cosine of mx plus, plus n squared cosine of nx over 2. Let's clean that up a little bit. OCD here. It's all right. Now what? What's a cosine of 0? So this is going to be a 1. That's going to be a 1. That's going to be a 1. So I'll be left with n squared minus m squared over 2. Because all these other things are constant with respect to x. So n squared minus m squared over 2. Nice. That one doesn't go? Nah, I don't think this one. Yeah, that one's a little. Yeah. Yeah. Let's see. Are you getting the idea about these repeated L'Hopital rule problems? I think we've done several, so I had in mind to skip problem number 44, or I had in mind problem 44, but I think I'm going to skip that and work on other indeterminate forms. Other indeterminate forms. So L'Hopital's rule is restricted to the 0 over 0 or infinity over infinity case. But there's other forms that we can apply it to if we're clever. So there'd be the 1 to the infinity power, or 0 to the 0 power, infinity to the 0 power, or 0 times infinity. And infinity minus infinity. So these are all different forms that if you write them in the correct way, that if you make them that is 0 over 0 or plus or minus infinity over plus or minus infinity, that you can apply L'Hopital's rule. But sometimes it takes a little bit of work. And I'm going to show you some of that work. Now the book, if you're looking at, what is it, Stadler, that website, their solution on this is going to be a little bit different than mine. And, you know, I can follow their solution. If you want to do it their way, that's fine. no problem there. But let's take a look at problem number 46 the way it is. Limit as x approaches negative infinity of x times the ln of 1 minus 1 over x. And wow, that one's kind of bizarre. If you look at the two terms involved, we've got x approaching negative infinity. So that term here is approaching negative infinity. At the same time, let's think about what happens to the log. You'll end up with the log of 1 minus this little piece. As x approaches negative infinity, what's going to happen to 1 minus 1 over x? It's going to go to 1. And then I'll have the log of 1. And the log of 1 is 0. So wow, there's your clash of the titans, right? Who wins? Multiply by 0, you get 0, or boy, multiply by infinity, wow. That's kind of bizarre. So I'm not sure if I have this one graphed or not. Let's take a look here on Desmos. I have that one queued up. Yeah, I do. Let's see what this looks like. Let's see if we can't make a prediction. So as you're going towards negative infinity, you're going out towards the x-axis. Well, it doesn't look like it's going towards 0 or infinity. It looks like it's finding a happy medium someplace. Looks like close to negative 1. But let's see it. Let's actually see it for ourselves. Now the trick in this one is right here. We're going to rewrite this as the limit as x approaches negative infinity of the ln of 1 minus 1 over x divided by 1 over x. So what am I doing? I'm dividing by the reciprocal of this. Right? So think about how we would, handle something like this. When you divide by a fraction, you multiply by the reciprocal, which would be multiplied by x over 1. And x over 1, well, it's just going to be times the x that I've got there. But when I rewrite it like this, as x approaches negative infinity, this term goes to 0. What about the term in parentheses here in the denominator? It also goes to 0. So now it's in a form for which I can use L'Hopital's rule. So let's apply L'Hopital's rule to this and see what that says. So this is going to be the limit as x approaches negative infinity. Now in the denominator, maybe it helps you to think of this as x to the negative first power. Maybe it's easier to differentiate it that way. In fact, it is easier to differentiate it this way. Because if you're looking at this, how do you have to differentiate this? What rule would you have to use? You have to use the quotient rule. Boy, that feels like a lot of work for such a simple little function, right? So, Eureka? Just stretching? Okay. All right. So we'll rewrite it like this. X to the negative first power. Sonia, what's the derivative of that, please? Derivative of x to the negative first power? Yeah. Negative x to the negative second power. All right, cool. So that's in the denominator. Well, we can, sure. We can think of this as being 1 minus x to the negative first. That might help out. Because the first thing that you're going to do when you differentiate the log of some function is take 1 over that function. 1 over 1 minus x to the negative first times the derivative of that. Right? The derivative of the outside is this times the derivative of the inside. Fadi. What am I going to get when I differentiate 1 minus x to the negative first? Negative 1 times negative 1 would be positive.
Oh, so positive 1x, or to the negative 2?
Yeah. X to the negative 2 power. So, okay. Before I start evaluating any limits, can you see any simplification that I can do here? Because the negative 1 multiplied the negative here. So you had a negative, negative times a negative, that's where it became positive. All right. So, any simplification? That and that. Thank you, Courtney. Both those disappear. Did the negative disappear? No. Limit as x approaches negative infinity, negative 1 over 1 minus x to the negative first. Can I write that x to the negative first as 1 over x? I think it might be easier to look at that and determine this limit here now. So I just went back to thinking this is 1 over x. This limit, negative 1 over 1 minus 0, is negative 1. These terms are fixed. This one goes to 0 as x goes to negative infinity. So it matches our graph. Jeanette, is there something I can help out with? Well, I mean, there's a couple ways you can think of this, but one reminder is on that handout I gave you in the last section, but we'll look at here. If you have a rational polynomial, so something where you've got, a polynomial in the numerator and a polynomial in the denominator, there's 3 cases when you're going towards plus or minus infinity. Case where the degrees are equal, then it's just going to be the ratio of the leading coefficients. But if the degree of the numerator is less than the degree of the denominator, then your limit is 0. So that's a different way to think of it. But just think of it this way. If you put in bigger and bigger numbers here, 10,000, or I should probably say negative 10,000, negative 10 million, this is going to get really, really small, right? And it's getting closer and closer to 0 as this gets really, really big. Yeah. Yes. Yeah. Sorry you missed that somehow. All right. There's a couple of ladies that came in late as well. Okay, so that's one of the tricks that we can use here. Yeah. Let's keep going. Yeah. Oh, Marissa?
When you did the 1 over 1 minus x to the negative first, and then times x to the negative 2, is that just the natural log rule?
When I went from here to here?
Yeah. Is that just the...
No, I differentiated. So to get from this step to this step, yeah, that's just the derivative of the natural log. So, yeah, and basically it looks like this. When you differentiate ln of u, you're going to get 1 over u times the derivative of u. So 1 over this times its derivative, and that's what we did here. So I wrote it like this, or I thought of it like this: 1 minus x to the negative first power, because it's easier to think of the derivative there. So I get 1 over that times the derivative of that, which is what we have here. Yeah, no, I appreciate the question. Thank you. Okay. Anything else on that one? These are good questions, and it helps us all out. Sure. It's a times. It's all right. Appreciate it. Anything else? These help out. Because people at home are going to be watching and going, "What's all that zero?" No, it's a times. All right. Thank you. So let's do problems. I'm going to call it problem 60-ish. And those are kind of like hints for you, really. If I'm that concerned about a problem that I want to do something, and make it easier for you, then maybe it's something you want to pay attention to. Limit as x approaches infinity of 1 plus a over x raised to the x. Now, I think in the book they have a b there, a bx in the exponent, which just makes it a little bit more annoying and tedious. It's not any less doable, but use your imagination for a moment and try and put in infinity. What's going to happen in the parentheses if I put in infinity? A in this problem is considered to be what? A constant. So no matter what number this is, if you divide a constant by infinity, what's that going to go to? It's going to go to 0. And the overall term in parentheses would go to 1. So I've got 1 to the infinite power. And again, it's like these two titans. Like, well, which one wins? 1 to any power is 1, but 1 to the infinity? That's bizarre. So let's figure out which one this is. Now, this is not in the shape of L'Hopital's rule, so I can't use that yet. So here's the trick. I'm going to think of this, we'll call that limit for the moment y. And I'm going to take the natural log of both sides. And because this is a nice continuous function other than 0, but since we're going to infinity, we can ignore the 0 part, I can interchange the limit and the order of the limit and the log. So instead of writing the log of the limit, I'm going to write the limit of the log. So let's get ln of 1 plus a over x, like that. Because this is a continuous function, you can interchange the order of the limit and the log. So we can get away with this. Now let's work with things here. And for the moment, it doesn't look like things got much better. It's like, okay, now you've introduced logs. This is getting messier. And Brandon's giving me this really skeptical look. It's like, I don't know, man. I don't know, parent. Where are you going with this? So let's think. The thing that you need to remember about logs is that there's properties of logs that can help us out, right? And in particular, that x comes out in front. This is something that a few of you would have done well to have used on your last exam. You use the properties of logs. There was a couple problems that were made much easier if you did these things first. So this is ln of y equals the limit as x approaches infinity of x ln of 1 plus a over x. Well, this is a lot like the problem we just did, isn't it? It's very, very similar to the problem we just did. What's our next step here? We can't yet. Because right now, this is of the form infinity, actually infinity times 0. Because the log of 1 is 0. Yeah. So limit as x approaches infinity. What was our trick in the last problem? We just did this in problem 46. Yeah, so we're going to write this as the ln of 1 plus a over x divided by 1 over x. Now, this is 0 over 0. It's in the right form. Right? Because if you take a look at the limit of the numerator, you get inside here that's 1. The log of 1 is 0. And 1 over x, as x goes infinity, that limit is also 0. So this is where you can apply L'Hopital's rule. Yes, sir?
Now that we got a test form, do we just ignore the ln of y?
No, we're not going to ignore the ln of y. We do have to account for this when it's all said and done.
So we're going to go back and multiply.
We're going to go back and do the unnatural log, or exponentiate both sides to get rid of the natural log on both sides. So yeah, there is some stuff to do. And if you notice, I've been careful to keep that ln all the way down, because you're right, we got to go back and take care of that ln. So this is the ln of y equals the limit as x approaches infinity. Now we just did this one in problem 46. When I differentiate 1 over x, I'm going to get negative 1 over x squared. And you can get that by rewriting this and thinking of it as x to the negative first power, and then differentiating that. So it would be negative x to the negative second, which is negative 1 over x squared. But I also got to differentiate that log term. And I guess it probably, I don't know, probably looks a little bit intimidating. It's like, oh my god. But this is, it's 1 over u, 1 plus ax, times the derivative of u. So the only thing we got to take care of there is to differentiate this term here in the denominator. So derivative of a over x, which you could think of as the derivative of a times x to the negative first power, so I get negative a over, or times 1 over x squared. Let me rewrite that a little bit neater. So, Ola, what kind of cancellation do you see here? All right. 1 over x squared cancels. What else cancels? Yeah, the negative cancels. Good. Are we okay with our cancellations here? Got rid of a couple ugly terms. That's nice. Let's take a look at what's left. It's the limit as x approaches infinity of a over 1 plus a over x. And that's my ln of y. Christian, what's that limit going to be, please? It's an a, not a 9. Yeah, a over 1. Or just a. So we did a lot of work, but all we got is ln of y. We want y. Emma, how do we get y from this? No, that's a lot harder than we have to work. Yeah, exponentiate both sides. E to the ln of y equals e to the a. What happens with these two? Cancel. So we get y equals e to the a power. And that's it. Well, these are constants. Or at least the right-hand side is a constant. So you wouldn't want to take the derivative there. So, well, it's a little bit messy right here. When we took the derivative, you had 1 over u times the derivative of u, and then those derivatives canceled each other out, along with the negative signs. It's a good question. This is not a problem with logarithmic differentiation. Okay, we're not taking the log on both sides and then differentiating. We're using this process to calculate a limit. So, yeah, we never differentiated both sides. So it's a good question, but yeah, I see the similarity. When you're using logarithmic differentiation, you take the log on both sides, but you follow it up with derivatives on both sides. Here we just use L'Hopital's rule, which is not really differentiating both sides. Now that actually is a cool result, and it actually applies to a couple more problems. It applies to problem 69. And applies to problem number 79. So if you look at it in the book, I think one of these problems, problem 60-ish, so in general, and like I said, I made it a little bit easier, the limit as x approaches infinity of 1 plus a over x to the bx. Now for us, I let b equal 1, but this limit would be e to the a times b. That's the real problem 60. Real problem 60 there. You know, it's a good question. I'd want you to show me some work on something like that. Yeah. But if you did know that limit, then you certainly could check yourself on stuff like this. On problem 69, this one would be e squared, because it fits into that form. You got a 2 in the numerator, that's your a, and b is 1, so it would be e squared. So that's nice. And likewise, over here, you can turn this one into a sub 0 times e to the rt. So, again, you get some nice benefits from it. Boy, somebody did a lot of work on this one. This one struck me. If you ever take a minute or two to read that in the book, that was pretty amazing. It talks about the light that the back of the eye receives, the retina, how it's a function of a couple different terms of which you can take the limit. But for us, I think we reached our limit. So let me give you some homework. So 9 through 27, 41, 43, 59, and 69. And for 47, I did you a little solid here. I calculated a few derivatives for you. Derivative of e to the x squared. Well, because you're going to have to do repeated. I did want you to do 47. You know what? Skip it. Maybe we'll make that an extra credit question. All right, but you got the rest of them? All right.